For this application, we used an i.MX Plus as the application processor that controls both the input devices, such as the camera and the rest of the boards, and the output devices like the HDMI display and the MIPI-DSi OLED display. Regarding our machine learning model, we used NXP EIQ toolkit to generate an EIQ project based on our faces dataset using the Python scripts provided. Then, we just need to open this project, verify that our dataset is okay, choose the type of model we will use, and adjust the training and optimization parameters to run it out of the board. We can modify learning rate, batch size, and epochs to train, among other options. Here we are training our model just for a couple of minutes. We will stop our training here just to show that the tool also provides a GUI to validate our model. Finally, we can visualize our neural network using the EIQ model viewer. Our last stage is to add this model to an application that will run on the board. For this, we use an NXP Python package called PIQ as base to develop our custom application. This package provides out-of-the-box machine learning examples, and all the source code is open and available in Code Aurora. The final step is to modify the source code, including our own model, to create our custom application. Here's our application listed as part of the PIQ package. We use an i.MX 1060 to run the voice recognition model and also as a hub for the tag reader board and the proximity time of flight sensor. This family of processors from NXP is well suited to run machine learning models due to its high performance ARM Cortex-M7 running up to 600 MHz and its extensive external memory interface options for NAND, eMMC, and Quad SPI NOR that overcome the disadvantage of having a low-density internal flash that most common M7-based MCUs have. Here we are gonna show you how to change the sample and how to add our custom voice commands. We have to install our SDK for the i.MX 1060. Once installed, we have to import an SDK example. So we select the board, look up on all examples, and select Maestro Demo. Then we import it on our workspace, look out for the BIT folder, open it, then the next folder, and look up for lib folder. And in this folder, we have to paste the model provided from NXP. And that's all. For the NFC reader, we use the ST25R3911B, capable of implementation of standard and custom protocols. Additionally, we used an ST time-of-flight sensor with the purpose of detecting when a person approaches the camera in order to activate the display, reducing the power consumption of the system. The BL53L0X time-of-flight sensor has the smallest package on the market today and can measure distances up to 2 meters, with a high immunity to ambient light. For the NFC and time-of-flight sensor, we just use the provided XQ software expansion libraries from ST. Here we can see a demonstration where our user meets the 3 security levels.
Hey Arrow, access. Hey Arrow, close.
And on this second demonstration, our user only meets one of the 3 security levels.
Hey Arrow, open.
Finally, here we can see the system working on a DSi OLED display. Hope you enjoyed our demonstration. That's all we have to show you for today. For this project, we will use an NVIDIA Jetson Xavier NX development kit, which has a GPU with NVIDIA's Volta architecture with 384 CUDA cores and 48 Tensor cores, and a NVIDIA Carmel ARM 64-bit CPU. The NVIDIA Jetson Xavier NX development kit includes a power-efficient module for AI edge devices. The Jetson Xavier NX development kit delivers the capability to develop and test power-efficient, small form factor solutions with accurate multimodal AI interface. The first step in getting started with the Jetson Xavier NX development kit is to write an image to the micro SD card. Please follow these steps on the developer.nvidia.com site. Once the image is flashed, we are ready to start our own application. NVIDIA has many resources and documentation available on the NVIDIA developer website. For downloadable documentation, software, and other resources, we can refer to the Jetson Download Center. NVIDIA works constantly to bring support to resources to speed up your application. NVIDIA has forums where the community and NVIDIA experts resolve any questions. Additionally, it includes Jetson's FAQs for answers to common Jetson platform questions, an ecosystem, services, and a Jetson wiki. Regarding the application deployment, NVIDIA has the NGC catalog. It is a curated set of GPU-optimized software for AI, HPC, and visualization. The content provided by NVIDIA and third-party ISVs simplify builds, customization, and the integration of a GPU-optimized software into workflows, accelerating development time for users. In our application, we used NVIDIA DeepStream SDK to rapidly develop and deploy our Vision AI application for traffic detection for people, cars, bicycles, and traffic signs. We just need to download the DeepStream SDK. Additionally, in the NVIDIA AI IoT Git, you can find many example applications and code to speed up your development. With NVIDIA Jetson Development Kit, we have two different ways to set up the system. A graphical interface with a display attached, as you can see in the video, and the second one using a headless mode when there is no display attached. For these second options, you'll need another computer and a terminal. Using a secure remote connection with the SSH, we connect to the Jetson Xavier Development Kit to remotely run the application. On the first chart, we can see the connection with the SSH to the Jetson, where we need to get the Jetson's IP plus user and the password to have remote access to the Jetson. Here we have the code to run our application and log files with the data and images recollected. The next step is to run the Python code. Using VLC Media Player, we open a network stream with the next link, including the Jetson's IP. We implemented a local backup to enable the possibility to save an image capture within a schedule. We can define the start hour and end hour times to back up images for the times with more traffic fluency. Using HTTP and JSON format, we send the data counters to Power BI to visualize it in real time. That's all we have for this project application. We hope you find it interesting and helpful. Thanks.
Starting with the demo part of the video, here we have an NXP LPC55S69 board using an NXP NTAG I2C+. This NTAG is connected to the LPC EVK board using a simple I2C bus. When the NTAG does not have a known value preloaded, the LED will flash in a bright white color. We will proceed to use the ST25 Android app so we can wirelessly transfer a known value to the NTAG, as you will do in a real-life application using NFC tags or cards. In this first step, we are going to write a red value to the NTAG, so we should expect a red flashing LED on the LPC board side. Now, let's try with the blue value. Just to double check everything is working correctly, let's load a green value to the tag and verify the LED flashing color. Red, blue, and green colors are pre-programmed to be known values for the LPC microcontroller, but What will happen if, for example, we load a yellow data to the end tag? As expected, the LED will flash in a bright white color since the only known values are red, blue, and green. In the second portion of this video, we will be recreating one of the previously shown programming example. Let's take the red case, but using a Tau glass FXR NFC antenna. Information is successfully loaded into the end tag in the same way as when using the NXP integrated antenna. With this POC, we want to show how simple it would be to implement a real-life application that writes a known value into an NXP end tag and fully develop a system to gain or restrict access to certain NFC tags or cards.
The hardware of this project consists of a local 2 IoT board based on an i.MX RT1060, a custom microphone board developed by the ESE team, a speaker, and a lithium-ion battery. We used MCU Expresso and NXP's SDK to develop the voice recognition application. We used the local voice examples as a starting point along with the Cyberon tool. NXP provides templates in each language that we need to import to the project. Then, using this tool, we modified the wake word group and created another group with all the custom commands. Testing and fine-tuning of the voice recognition algorithm was also done using this tool. Additionally, sections of the source code were modified to enable these commands and to add the feedback sounds. To add the Bluetooth functionality, we used another example as reference. In this example, we modified the properties of a single Bluetooth characteristic to send the wake words and custom commands and added a function to send the notifications once the voice command is detected. Then, we merged both projects. To test the Bluetooth functionality and receive the commands, we developed a Python application that scans and detects the device, starts the connection, and activates characteristic notifications. Finally, the commands are shown in a GUI. We can provide all the source code used in the project. Just contact the ESE at arrow.com. We are about to show you a representation of how our application will work.
SAM project.
Hey Samcar, ignition. Hey car, hazard lights on. Samcar, drive. Hey car, warning lights off. Hey Samcar, accelerate.